folks, Ms. Gosling here. In this video, you're going to learn about free fall. By the end of the video, you'll be able to define free fall, and you'll be able to apply the kinematics equations to free fall scenarios. So let's go ahead and get started. So we're going to start by defining free fall. Free fall is defined as the motion that occurs when the only force acting on an object is gravity. So what that means is I have an object falling through the air, and the only thing making it fall is gravity, and nothing is helping it stay up or anything like that. So unless otherwise stated in the problem, we're going to assume that our acceleration is negative 9.8 meters per second squared. And that is our acceleration due to gravity. The second thing we're going to assume is that our u is 0 meters per second. Now, I'm actually going to change this a little bit, because what I want to say is that our speed is 0 meters per second at the highest point. So if I'm standing on a cliff and I drop something, then u is going to equal 0 meters per second. But if you are standing at the bottom of a cliff and you throw something up to me, it's not going to have an initial velocity of 0 meters per second, but when it reaches its highest point, here, it will have a velocity of 0 meters per second. So that's going to be kind of our big difference here. Our big thing here is that our acceleration is always going to be negative 9.8 meters per second squared, and then our velocity is always going to be 0 at the highest point in the object's motion. Usually it's at the very beginning, because often we're going to have problems where things are dropped, but that will not always be the case. For example, if I were to throw a ball up in the air, it would have an initial velocity that was not 0, but its velocity at its peak, at the highest point of its motion, is going to be 0. So let's go ahead and solve a couple of free fall problems, because I think that'll make things clearer. So let's look at example 1. This past summer, my sister Ellie decided to go bungee jumping. If she jumped off the bridge with an initial velocity of 2 meters per second up and was in free fall for 3 seconds, what is her velocity after 3 seconds? So I'm going to go ahead and start listing out my SUBOT table. Now, since Ellie is in free fall, that means I can use my free fall assumptions. So first of all, I know that her acceleration is negative 9.8 meters per second squared. I also know that her velocity at the highest point in her motion is going to be 0. However, this actually doesn't relate to my problem at all, because we know her initial velocity and we don't want to figure out her highest point. So let's go ahead and put in the other info that we know. So we know that her initial velocity is 2 meters per second up, and I'm going to go ahead, I'm going to draw this as my sister going bungee jumping. Her initial velocity is 2 meters per second up, and the gravitational acceleration is going to be negative 9.8 meters per second squared down. So that means that I need to define up as being positive. So I can say that her initial velocity is 2 meters per second without having to worry about writing in directions. I also know that she was in free fall for 3 seconds, so that's going to be my time. This question is asking me to figure out her velocity after 3 seconds. So V final is going to be our question mark. Now, this is not her final velocity, but it's the velocity at the very end of our problem, which is why we call it our final velocity. Right? She's going to continue falling after 3 seconds, but we don't care about what happens after that. Now I can cross off my extraneous information, which is going to be S, which is her displacement. One thing to keep in mind is sometimes displacement you'll see the word height, and that would be something that would suggest that you're looking for displacement. We don't need to worry about that now, though. So I'm going to go ahead and cross off all of my equations that include displacement, and I'm going to use the equation that does not. So I know that V is equal to U plus AT, so I'll go ahead and plug in some numbers in my sub and solve stage. So V is my unknown, so it's going to stay a variable. U is 2 plus my acceleration, which is negative 9.8, times my time, which is 3. So when I stick all that in a calculator, what I get is that my velocity after 3 seconds is negative 27.4 meters per second. And there you go. That is going to be the answer to this problem. So let's look at a slightly more complex example. This is a very IB style problem. So this is something you're going to want to take a little bit of a look at, really make sure you understand. So object A is located directly above object B, and they are separated by a distance of 5 meters. Object A, and what I'm going to do is I'm going to go ahead, I'm going to make object A is going to be blue, and object B is going to be green. So object A is thrown downward at a velocity of 1 meter per second, and at the same time, object B is thrown upward at a velocity of 1 meter per second. When do the two objects meet? Let's go ahead and figure that out, and I'm going to start by drawing a picture. So here's object A, and here's object B, and we know that they are 5 meters apart. So I'm going to go ahead and draw that in. I know that object A has an initial velocity of 1 meter per second down. And what I'm going to do is I'm going to go ahead, I'm going to draw my frame of reference up here in the corner. I'm going to say that where object B starts is 0. So that's going to be my origin. And I'm going to say that up is my positive direction. So that way in my problem, I don't have to say where 0 is, and I don't have to say where, I don't have to use ups and downs. I can just use positives and negatives. So my acceleration my initial velocity for A now is going to be negative 1 meter per second because it's down. And my initial velocity for B is going to be positive 1 meter per second because it's going up. So we want to figure out when the two objects meet, and that is going to be our answer to our problem. One thing to know is that we know that they're going to be in one place at one time when they meet, right? So that's going to be kind of our trick to solving the problem. But to do that, before I do that, what I'm going to do is I'm going to make my SUVOT table. And I'm going to make a table for A, and I'm going to make a table for object B. So we've got kind of a double SUVOT table going on. And this is a trick you're going to want to learn, guys. If you have more than one object, you're going to need to make one table for each object. So let's go ahead and do that. So we know that object A is located directly above object B. So we don't actually know our displacements for A and B, but we do know their initial positions, and we know that we want to have a final position that's the same for each of them. So for A, I know that A's initial position is 5, and I'm going to go ahead and say that X is what we're going to call our initial position. Similarly, I know that B's initial position is 0, and B and A both end at the same final position X, because that's what it means for them to meet. I know that they are both in free fall, so that means that they both have the same acceleration of negative 9.8 meters per second squared, and that is because this is, again, we know it's a free fall scenario. Similarly, I know both of their initial velocities. So object A has an initial velocity of 1 meter per second down, or negative 1 meter per second, and B has an initial velocity of 1 meter per second up, or positive 1 meters per second. And what I'm trying to do is I'm trying to find the time where the two final positions are the same. So this is going to be a little bit of a multi-step problem. Let's go, so stick with me here. I'm going to start by crossing off my final velocity because I don't care about it. And I'm going to go ahead and cross off every equation that includes final velocity, leaving me with this equation here. So I'm going to write that equation for A, and I'm going to write out that equation for B. So I know for A, x minus 5 is equal to negative 1 times t plus 1/2 times negative 9.8 times t squared. Or x equals negative t minus 4.9 t squared plus 5. And I can go ahead and I can do the same thing for B. So I know that x minus 0 for B, my displacement, is equal to 1 times t plus 1/2 times negative 9.8 t squared, or x equals t minus 4.9 t squared. Now this problem is asking me to find when my objects meet. So what I want to find is my time. So what I'm going to do is I know that this x and this x are equal to one another. So that means that the right sides of each of my equations are also equal. So I'm going to go ahead and write that down. So negative t minus 4.9 t squared plus 5 is equal to t minus 4.9 t squared. And this looks really ugly, but what you'll see is both sides, I have a negative 4.9 t squared. So if I add 4.9 t squared to both sides, that whole thing is going to cancel, giving me a much prettier equation. And I'm going to go ahead and I'm going to switch this equation to all in black just because it's a little simpler. So what that gives me is negative t plus 5 is equal to t, or 5 is equal to 2t, or t is equal to 5 divided by 2, or 2.5 seconds. And there you go. This is how you can solve a slightly uglier question. So takeaways. Free fall occurs when the only force acting on an object is gravity. And our third takeaway is also something you've already seen before. So for takeaway 3, in free fall, we can assume a equals negative 9.8 meters per second squared, and our velocity is equal to, 0 meters per second at the highest point. This middle point here is a little bit new, and that is that free fall doesn't happen in real life because there was always air resistance. So this is not something I talked about earlier in the video, but I want to make sure you take this away. Because air resistance is always around, because there's always air on Earth, we're not going to have free fall happen in real life. However, because it is a good approximation for most objects, we're going to be able to use it to still solve problems. So that's just something to think about as you are working through problems in this unit. So there you have it, folks. Best of luck and happy solving.